Lab 2, motion of a falling object. So the purpose of this lab is to describe the motion of a falling object using Newton's second law. The principles used for the velocity update formula, two different versions of the position update formula, one for when force is constant and one for when it's not. And the drag force for a constant v is multiplied by speed squared. This lab shows the impact of drag on the simulation of a falling object and its equivalent in reality. So, for the initial conditions of the lab, the system is a waterlet piece of printed paper. The surroundings are earth for the gravitational force and the air for the drag force. The system is initially at rest. So, for our experimental data, we can see the general shape that we want for the simulation of position versus time, which is roughly parabolic. And the important information from the data over here is that the experiment lasted 0.433 seconds. The initial y value is about a millimeter below the origin, and the final y position is just a smidge over a meter below the origin. So, for the simulation without drag, our ball has a mass of about 4.4 grams. Our delta t is 0.033 more frame. Gravity is 9.8. B is 0 because there's no drag. And the simulation will last 0.433 seconds. The net force is equal to the mass of the ball times gravity. Our velocity update formula is equal to the initial velocity plus acceleration times time, so just negative g. And then our position update formula is for when there is a constant force, because gravity is constant and it's the only force acting on the system. So that means it is initial position plus ball's velocity times delta t plus 1/2 acceleration, which is gravity, times time squared. And then for our arrows, we only have gravity affecting the system. So here you can see only gravity is affecting the system. Because there's no drag to counteract gravity, our simulated ball ends up at about negative 1.2 meters. And velocity versus time is constant because only gravity affects the system. So for the simulation with drag, we now have a b value. Our drag is equal to that b value times speed squared. This force drag shows up in our velocity vector. And then for our position update formula, we have to use the one for when force is not constant because drag is not constant. And then for our arrows, we now also have a drag arrow, and this 0.15 is just an arrow scale. So, as we can see here, our drag force never equals the force of gravity. This is seen in our velocity versus time graph because we never hit terminal velocity. And our position versus time graph is equivalent in its final position to our experimental data. So for our analysis, like I said, the drag simulation and the experiment end up at the same y position, and the one without drag ends up lower because there is no drag force to counteract the force of gravity. The error here is that our simulations don't actually start at the same place as our experiment due to a coding error, and the angle of the camera was also not accounted for, which could throw off our experimental results and thus our simulations. So the simulation with drag does show a prediction of terminal velocity because the slope starts to level off, but because the experiment never reached terminal velocity, the simulations didn't either. When terminal velocity is reached, the net force on the system is 0. And the terminal velocity to throw an object has to be greater, as the drag would have to equal both the force of gravity and the force of throw, which is seen in our throwing velocity versus time graph on the left.